Welcome. In this video we will discuss limits as we tend towards infinity. Let's begin our discussion by talking about this function f of x equals 1 over x. Fill in this table for different values of x and see what happens to the value of f of x as you evaluate the function. So if you did that, you should have got the following: 0.2, 0.04, 0.008, so on and so on. And the question is, what happens to f of x as x gets bigger? We can see f of x is quickly shrinking, getting closer and closer to 0. So as x tends towards positive infinity, f of x is tending towards 0. So the next question is, what similar functions might do the same thing? Well, really just any function where the numerator is a constant and the denominator is growing. So x, x squared, x cubed, even maybe 1 over 2 to the x. So in this lesson, we're going to discuss that very thing. What happens to a function as x tends towards infinity? Last class, we talked about what happens when x tends towards a certain number. So we're changing it up this time, talking about x going to infinity. So we're also going to be able to determine the vertical and horizontal asymptotes of any function by determining these limits. And then this will build us up to next class when we talk about infinite sequences. We noticed from the do now that this function gets smaller and smaller as x gets bigger, right? So we would say, and this is notation, limit as x approaches infinity of f of x equals 0. So it turns out that any function in this form, we have a constant divided by x to some power, will tend to 0 as x tends towards infinity, which is pretty intuitive. So suppose we're given a function and we want to know what is the limit of that function as x approaches infinity. How do we figure that out? Well, we're going to use the fact that c over x to the n always goes towards 0. We're going to do a little algebraic trick, and then we're going to eliminate terms of this form to figure out what is the limit. So let's try an example. Here we're asked to find the limit as x approaches infinity of this function 2x plus 3 over x plus 1. So first what we do is we divide all of the terms by the greatest power of x. So in this case, the greatest power of x is just x. So we divide everything by x, and we get the following. On the numerator, 2x divided by x plus 3 over x. Denominator, x divided by x plus 1 divided by x. Obviously, x will cancel here and give you 2 and 1, plus 3 over x plus 1 over x. Now it's of the form that we want, so then when we talk about tending towards infinity, all of the terms of this form will go towards 0. So this will go to 0, and this will go to 0 as well. So this tends to 2 plus 0 over 1 plus 0, which is 2. So we can say the limit of this function must be 2. Okay, so what does this have to do with vertical and horizontal asymptotes? Well, the limit as x approaches infinity of f of x often describes the horizontal asymptote of a function. So look at if I graph the function we just dealt with, 2x plus 3 over x plus 1, this is what it looks like. You can see that as x tends towards infinity, technically also tends towards negative infinity, but in this case tends toward positive infinity, the graph is getting closer and closer to 2, but never actually touches it. So that's the idea of a limit. But what about the vertical asymptote? So that's horizontal. Vertical asymptote is going this way. How do we find that number? Well, it just has to do with the denominator. What values of x make the denominator equal to 0? And we know that would be undefined. So we just set the denominator equal to 0, and we can see that if x is equal to negative 1, we're going to get 0 in the denominator, so that is our vertical asymptote. Let's try an example. Determine the horizontal and vertical asymptotes of this function. So first, we'll find the horizontal asymptote by dividing by the greatest power of x. So in this case, that's x squared. So we divide every term by x squared. When we do that in the top, it will cancel here, and the denominator will cancel there, and we're left with this, negative 2 over 1 minus 1 over x squared. Then using the same idea, as x tends towards infinity, this term 1 over x squared will go towards 0, and so we'll simplify to be negative 2 over 1 minus 0, which is negative 2. So our horizontal asymptote is y equals negative 2. And then what about the vertical asymptote? Well, we set the denominator equal to 0, and we solve for x. So in this case, that would be x squared minus 1 equals 0. Solving, we see that we actually have two vertical asymptotes, x equals positive 1 and x equals negative 1. So that's our answer for the vertical asymptotes. And if we graph the function, you can see it does indeed have all of these things. Here's your horizontal asymptote at y equals negative 2, and then you've got one vertical asymptote at x equals 1, and you've got another one at x equals negative 1 on this side. There are a couple important special cases to mention. The first one is if the numerator of a rational function, so something with a polynomial in the top and the bottom, if the numerator is greater than the denominator, you're going to have something called an oblique asymptote. So for example, the function x squared plus 1 over x. If you simplify that, it's actually just equivalent to x plus 1 over x, which as x tends towards infinity will tend toward x plus 0 or just x. And you can see that graphed over here to the right. You've got kind of like a slanted asymptote that's known as an oblique asymptote. So that only happens if the numerator is greater, the degree of the numerator is greater than the denominator. And so our asymptote is y equals x. Another special case is if the numerator can be simplified and something will cancel. If that happens, then you won't, depending on the function, you may or may not have an asymptote. You may just have a hole in the graph. So keep that in mind. All right, that's everything you need to know to start working on the practice assignment. Let me know if you have any questions.